think realistically, this is what this is like, right? You get somebody with the expertise to do it. Like, how do we all of a sudden have a sophisticated
And then you have a programmer
model?
that's in
Right.
Oh, really? Yeah, so it's right.
That would be fine.
Does anyone need a handout? Are there any more handouts?
Yeah, there's a bunch. Do you need one?
Yeah. Just gonna pass them down. There's more handouts.
Yeah, I mean, I think it's, I don't know how many other people have the same situation. Let's see if we should get tomorrow. I have two.
Did we have a good weekend?
Thank you.
I did. It was good. Trying to work on more sleep. It's not working, but I'm working on it.
Do you have trouble sleeping?
God.
Oh. Just not enough time.
It's finding time to get enough sleep. That's the
Do
issue.
you have kids?
Yes. Did you get one? They're older, so, but my son, who will be 8 next month, will sleep late on weekdays for school, but get up at the crack of dawn on the weekends. And I'm like, dude,
That's what we used to do. Be like right in their bed.
I'm like, dude, come on, man, you're killing me. So, was anybody able to find an example of logistic regression in the literature that you would be willing to share with the group and discuss? I don't want to start out collecting. We're big boys and girls here. Come on. Anybody find anything? Nothing? Something? Something you think is logistic? Something you don't know is logistic? No? That's how to shut up.
Yeah, I was gonna say.
I figured it out already. All right. I said I figured out how to make you guys be quiet. Just ask you a question. Nobody? Look at it. Now they're all burying their faces in their electronics here. It's so funny. You're like, this makes a lot of sense. Yeah. All right. Okay. Okay. Well, here I want to finish up, or at least get through as much as we can of logistic regression today. We'll see if we can pick up. Does anybody remember where we left off on Thursday? Was it about here-ish?
Yeah, we can put it a little bit about there.
Okay, all right. Well, that's a lot of math. It's probably kind of confusing. Oh, we did this. I know we did this. Okay, so this is from that data that we have. This is actually how we would do the logistic regression in Stata. So the command is really simple. It's logit. There's actually a couple of ways to do it. One command is the logit command, which is actually, I think, the most useful. And you could also do it using the logistic command. The logit command will kick out coefficients, logits, whereas the logistic command will kick out odds ratios. Okay? So, if you remember, this was a heart attack. We're trying to predict the odds of heart attack, the relative odds of heart attack for comparing males to females. A heart attack here, all right? So here we have an intercept, right? And how would we interpret an intercept? It's just as if we were to interpret that intercept just like we did with linear regression, right? So that's the expected value of y when all the x's are 0. So in this case, when x is 0, we're dealing with females, right? So if this becomes the logit, or the log odds of a female having a heart attack, this is the incremental effect, or the change in the effect of those log odds for a male relative to a female. And this is stuff that we've seen before. The only thing that's a little bit different is instead of a t, we get a z. Right? So the same way we're going to divide our standard error into our coefficient to get our z-score, and we have our confidence intervals here. Right? And now we have, just like we did in linear regression, now we have an equation. Right? But notice here, this is going to give us our log odds. This gives us our log odds. Right? So let's, you guys, I gave you that code last week. This is the data we had. Is this too low for you guys to see? It's the output that's on the handout. Okay. So let's take a look at what's going on up here, right? This is sort of kind of an important thing to look at, what's going on up here, right? So just like when we did linear regression, the first thing it's going to tell us is how many observations went into the model. Then we have this likelihood. LR stands for likelihood ratio. A likelihood ratio. And remember when we did regression, or in ANOVA, we had an F test. And for regression, the F statistic tested the overall model and said, is this model better than nothing? Right? Is this model better than nothing? That's what this likelihood ratio test is testing. So the first thing it's going to do is it's going to fit a model with no predictors in it. Right? It's going to say what's the average sort of log odds of having a heart attack. Then it's going to fit this second model using male as a predictor. Right? So in that sense, we have one model nested within another model. Does that make sense? So we have this idea. So okay, we got that. This is a likelihood ratio. Okay, and this is the p-value associated with this likelihood ratio test. The likelihood ratio is that's chi-square distributed. I'm not going to get into too much detail unless you want me to, right? Because there's some more stuff we can do that will get into the detail, right? So this is the probability. This is the p-value associated with the question: is this model better than nothing? So here we have this p-value that's 0.6 or 0.7. Not significant, right? But that's okay because we're just using for teaching purposes. And the other thing here is we have this pseudo R squared. It's a pseudo R squared. So it's not a real R squared like we had with regression and correlation and all that, but we would try and interpret it very similarly. The reason that it's a pseudo R squared is because it's really not dealing with variance per se, but we're going to try and interpret it the same way. Okay? So that's this stuff here. And let's pretend for a moment that this was statistically significant. Then we would go on and interpret these things. Now recall that these are log odds. These become log odds. If I want to get the odds ratio from the model, what I'm going to then do is then I'm going to type in logit, comma, OR. So by doing this OR thing, it's going to take these logits and it's just going to exponentiate them. So so it's going to say E 1.69. It's going to exponentiate that value to get this value. If I exponentiate this value, I'll get this value.
Is there a reason you like doing the coefficients first?
Yes.
That's fine.
Yes. Good question. The reason for that is I can't add these together.
Okay.
All right. These are not additive. These are additive. From logits, if I instead of so how much do you guys know about logits? Not a lot? Okay, so what's easier, multiplication or addition?
Addition.
Addition's a lot easier. So If I take the log of two numbers and add them together, that's the same as multiplying. So when I get into more complicated models and I want to come up with predicted values, I can't add my odds ratios. I have to add my logits, come up with a y hat, and then exponentiate that.
When you say, when you add the log of two numbers, it's like multiplying what?
The two numbers.
Just multiplying the two numbers.
Okay, all right. So here, let's interpret this, right? So now we can interpret this. So now if I look at this constant, this is when x is 0, so I must be referring to females. So since this is an odds ratio and it's less than 1, this says that the odds of a female having a heart attack are less than 50-50. The odds, I would interpret this directly as the odds of a female having a heart attack is going to be like 0.42 to 1. Instead of, usually we say like 3 to 1, 4 to 1, 5 to 1. Here it's 0.42 to 1. Not 2, but TO. Right? So the probability of a female having a heart attack is less than 50%. Okay? Now if I look at this male, the coefficient for male, right? This is going to be, what is the effect of going from female, which is 0, to 1 male? The odds of a male having a heart attack are 5.4 to 1 as compared to females. Right? I could also have another interpretation and say that I can take this value minus 1 and say that the odds of a male having a heart attack are 444% higher than that of a female. Okay. So if the odds ratios were 2 to 1, how much higher is the male to have a heart attack relative to a female? 100%. Right. So that's why we're going to subtract 1 from that number. Okay.
Is this output you would have gotten if you just done logistics?
Yes. Yes. So let's do that. I'm going to point to my computer. Can you see where I'm pointing? Oh, I'm going to kill myself over here. So the commands are coming up over here. That's what I'm typing. So that says logistic, HA, male. So if I type in logistic, HA, male, it gives me the odds ratios directly without doing the other stuff. Right?
All the other numbers are the same.
The logits, it doesn't give me the logits. Right?
Can you do logit, HA male, comma, OR?
Pardon?
Can you do logit, HA male, and then comma, OR?
Yeah, that's what we did to
same?
get the previous table, yeah.
Oh, okay, instead of 2 steps, I usually do one.
Yes, you can. Yes. So the other way that we could do this is logit, HA, male, comma, OR, and we get the same values.
You don't get the coefficient then.
Pardon?
They give it to you right above the coefficients.
They give the coefficients right
Oh, no, it's not above.
No, they're not here. These are the odds ratios. All right. But first, when I report in a table, when I report this stuff in a table, I report this. I report my logits, and then what I do is I add another column, and I put the odds ratios here.
Can you repeat again? I know you just said it, but what I'm using the coefficient for?
Okay,
From the odds
so
ratio?
these coefficients, these are our actual model. So if I were to write down the equation, I have yi hat, where yi is going to be the logit, the log odds of having a heart attack in this case. That's what yi is here. It's a log odds. Is going to equal This is my prediction equation, right? The reason that this becomes the coefficients, the logits are helpful, is now if I want the probability or the log odds of a male, the overall log odds of a male of having a heart attack are going to be 0.85 plus 1.69 times 1. I have to add that together and exponentiate that. This gives me the odds of a male having a heart attack. The 0.54 that we saw are the incremental odds, or the change in the odds from a male compared to a female. Right? But I can't add those odds together, those odds ratios together.
So, I mean, just the point of putting that into a paper is so that people reading it know what the model is.
Yeah, yeah.
But that would, like, it's not like you can get any information.
Yes, you can. Because if we add more variables to the model, like age, sex, race, right? And then you want to figure out, okay, given this model, what's the probability that a black female who's 32 years old, what's the problem of that person having a heart attack?
Okay.
To do that, you'd have to plug in all the values from the logits, add them together, and then exponentiate that to get that person's odds. Otherwise, you would say, well, you're male, well, you're female, so your odds are less. But you're an older female, so then your probability goes up because you're older. And then you're black, so your probability is going to go up. And that's not how this works. It's what's the probability, what's the joint probability of all of these
Can't
things
you get
happening.
that if you do that first and then do your logit comma OR?
Yes.
So that
You
would
get
be
the
the
odds ratios for the coefficients, but you won't get the odds for the black 34-year-old female.
Okay. So to do that, you have to add them up
Yes.
and then do
Yes. Yes.
I mean, you could do it from the odds ratio, just take too much math, right?
Right. It's a pain in the butt.
So, but you said if I did e to the 1.69, then you get the 5.44.
Mhm.
So that's the odds of a male having a heart attack compared
To a
with a
female.
female. But if you do e to that,
Mhm.
that's, what does that mean?
That's the odds of a male having a heart
And
attack.
has something to do with females.
Correct. Not the relative odds or the odds ratio. It's the odds of a male having a heart attack.
Is what?
It's the odds of
What
a
is
male.
not the 5.22, because that's relative to.
That's the relative odds. So to
What
that,
would-
this becomes the odds of a male having a
Oh,
heart
just,
attack.
oh, okay, which is like 5.4.
No. The 5.4 are the incremental odds.
Well, I just did log like 1.8 to the 1.69, but I guess I didn't.
Yeah, that is 5.44.
Right.
This?
No, if you do that, that's not 1 point. That's
Yes.
not 5.44.
Okay. So what happens when you do this?
Hold on, I did it wrong.
Why are you?
That's 2.32.
2.3?
Yeah.
Remember last week we had a table that looked like this? I think we had heart attack, yes, heart attack, no, and then we had males and females, right? And we had like, it was 3, 7, 7, 3, and we computed the odds of a male having a heart attack, irrespective of females. Do you remember what those odds were?
7
Which is 2.3. Let's back up. Yes. Okay. So remember we did this? We said, what's the probability of a male having a heart attack? We didn't care about the females for that question. So that's going to be 7 divided by 10, which gives me to do 2.33, right? I can get that same 2.33 by doing this. right? I can't add together, if I were to add together those odds ratios,
But we can multiply them.
pardon?
But we can multiply them.
This is what happens when I... Yeah, this is what happens when I multiply them together. I get back to those odds. That's easy to do when you have simple models. When you get more and more complicated models, it's easier to do. So what I do when I report stuff like this in journals, is I report the logit. I report this. I report the logits. And then what I do is I add another column for the odds ratios. And whatever the heck it was, I don't remember what it was, 42. Right? And then in my paper, I explain how I got this odds ratio from this table. A lot of people don't get it. So I actually say the odds ratios for a male relative to a female will be, and I will actually write this in my table. E to the 1.69 equals 5.44. I'll actually write something like that in my table, in my paper, in the prose of my article to help bring people along. Right? And then I will say, for example, when we do a more complicated model, I'll actually do an example. So to interpret this model, I multiply all the coefficients together to get the odds of a black 34-year-old female having a heart attack. And I show them how you need to use all of these exponentiated to get that person's odds of a thing. And then what I will do, what I will often then do, is that for my reader, because I'm not assuming my reader is trained well, is then I'll show them how to turn these odds into a probability, which we know how to do that too. Okay. I've received reasonably good feedback from editors, from most journal editors, and some people have actually, sort of shot me an email after an article has been published. They said, thanks for that little explanation. I never knew how this all put together. That's true. So, a lot of people just take it for granted that, oh, this is how you interpret it. They don't know. Okay.
So can you send us an example of that?
Yeah, sure. Yeah, absolutely. Okay, so anyways, this becomes the equation that we got. And then remember what we're talking about here, these are now log odds, right? These are log odds. So I take these odds and turn them into a probability. So it's 1 over 1 divided by the odds. Right, okay? Okay, now because we coded male and female as 0 and 1, right, that has an interpretation. So this gets back to the idea of a contrast matrix. So when you use dummy coding, right, I can have more than one value. I could have had like race, which could have been, Caucasian, African American, Latino, whatever, and then have an other. Right, so in my regression equation, I would have 1, 2, 3 predictors, and then an intercept. And just like in linear regression, those coefficients become the logits of success of the one value as compared to the reference group, just like we did with linear regression. And I have another example of that in the next thing I want to talk about. Right, but because we use dummy coding, You know, that idea of X1, X2, and X3 that we talked about last week, it's exactly the same concept. I could also have used deviate coding or that Helmert coding like we did before too. So everything that we did with respect to the contrast matrix in linear regression holds here because this is linear regression after we transform the error term. Okay? Okay, so that's that.
Tim,
Yes?
when you get a probability from a logistic regression, is the probability then like an adjusted probability, or is it just
It's the predicted probability.
predicted probability from the model?
Yeah, so you would say it's actually technically, it's what we refer to as a conditional probability. It's conditional on these predictors and the value of those predictors.
I mean, because you could take like the data and just say like a proportion of, you know, blah, 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 you know, like receiving treatment,
Yep.
blah, is, you know.
Which is what we
X%.
did, which is what we did in the first place. So we had 10 heart attacks, 10 non-heart attacks,
Yeah.
and the crude probability would, well, you got a 50-50 shot, right? So then we asked another question, a more specific question. We said, what's the probability of having a heart attack given you're male? When you hear somebody say given, that really means conditional on this, that, and the other thing. So the more things that you add into the model, the outcome is conditional on those values.
So is it like conditional, like you're holding all the other variables constant?
No,
Or-
because you're going to get a probability for somebody. So what I want to do next is we're going to fit, instead of a simple, what we refer to as a simple logistic regression outcome and then a single predictor, we're going to do a multiple logistic regression. Then when we get coefficients and odds ratios for each of those coefficients, those would be adjusted coefficients, just like we did in multiple regression. So the answer to your question is not quite what you said, but yes, in the case where we have multiple predictors and I interpret the effect of each predictor, it's adjusted for the other predictors in the variable. But in the end, remember what we're doing is we're adding up all of the coefficients to come up with that one number, that predicted value. So that's not a conditional, it's conditional in the sense that it's all values in the model. Okay? Okay. So what I want to do next is I want to start building a model. All right? So this is the handout that I gave you today, and if you don't have a copy, there should be stuff floating around here somewhere. Okay? So this, we have pediatricians here, don't we? Yeah, okay. Pediatricians? All right, so here's a data set. Here's a data set where I'm interested in studying or coming up with an equation to be able to predict low birth weight of little guys. Okay, what predicts low birth weight of little people, straight from the factory? Okay? Okay, so that's what we're looking at here. So we're going to deal with this kind of a famous data set. It's used a lot when people teach logistic regression. And this data set you can grab from the Stata website by using the web use command as you see on the thing here. Okay. All right. Well, the first thing I'm going to do is I'm going to look at my data here. And this is just a simple frequency table, right? Because this is data analysis. Everything that we did before, where you would look at your univariates, I believe you refer to as your table 1 material, you do all that too, right? But we're going to skip that part, and I'm going to assume that when you get a data set, you're going to create your table 1, and you know why we create table 1, look at outliers, are there any missing data, blah, 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 blah. We're going to do that, all right? So here's what we have here. We've defined low birth weight as some little person weighing less than 2,500 grams at birth. subject to your definition, this is how it's been operationalized here. Okay? And in this table, we have about a third of the little people who are low birth weight, who are born meeting our criteria for low birth weight. Okay. First of all, before we go into the logistic regression, let's talk about this. We've taken a nice continuous variable, and what have we done to it? We've created an artificial dichotomy. We've created an artificial dichotomy. So, we need to start thinking, that'd be the first thing I would look at, one of the first things I need to think about. Even though it's low birth weight, we've taken a continuous variable and we have made an artificial dichotomy. You know, have you guys looked at diabetes and cholesterol, the clinical interpretation of those over the past 20 years? They go down, 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 down. So what may not have been low birth weight 10 years ago may be low birth weight now, because we've taken this continuous variable and we've come up with this artificial copy. Right? So when we interpret articles, we need to think about these things. Right? Okay, with that being said, this is all we know, and from here we can actually come up with the odds of, what's the probability of having a low birth weight? It's 31. Right? And from that we can come up with an odds, right? 1 over 1 plus 0.31. That would be the odds of having a low birth weight. Okay. All right. Well, the first thing I'm going to do is I'm going to just examine, I'm going to do a simple logistic regression where I'm going to look at the relationship between maternal age and probability of low birth weight. Right? The other thing I'm going to do is that I'm going to take these estimates and I'm going to store them for later, because I'm building a model. Remember before we talked about, we took our variables and we classified them as, like, first we had demographic variables and then we had clinical outcomes, which we don't think the intervention will have an effect on, and then we finally had our intervention, right? So that's in a sense what I'm doing here. So I'm going to take the estimates from each of these successive models, and then I'm going to store them for later in the memory of the computer. Right? That's what these two things have said. Well, this is going to do the logistic regression, and then I'm going to store that output into. I'm going to store that output. Bada bing. Okay. These are logits. So, just what can we say so far? Let's say that we got 189 observations, right? Here's our chi-square based on 1 degree freedom. And this is our p-value for that chi-square, which says, is the model any good? And we say, does not meet our statistical criteria for good. Right? Further, the pseudo r squared is anemic. We need this low birth model needs some weight put on it. We need to make it more robust so it can thrive. Am I using the right language? Yeah. So it can thrive and develop normally. All right. Okay, so let's look at these anyways here. Okay, so we have this idea of age. Age is negative, right? This logit is negative. So without doing the transformations and stuff, right, without exponentiating any of that, what can we say? As age goes up, the log odds of birth weight goes down. So older moms tend not to have low birth weight babies. Okay, make sense? Okay, we don't know what that is. If we wanted to figure out what the odds of, how the odds change, we would simply exponentiate that value. Okay, and our p-values are, they're huge, which agrees with this, so, okay. But Stata's got some really cool commands in here that I want to share with you that are not on your sheet. I'm going to do these in turn. One command is called estat classification
Where does it store it?
in memory. Who asked that question?
I did. Like, where do you find it?
In memory, you don't. It's in the chips.
So why,
I do
what's
variables
the
are
point?
pretty
What's the point?
Because I'm gonna add another variable to the model
Oh,
and do that likelihood ratio test.
okay.
So instead of having to write it all down and do all that math myself, I'm just gonna have this computer say, hey computer, remember this.
So it's like a clipboard?
It's a clipboard. It's like clipboard. That's a good way of thinking about it. Yeah. It stores it in memory.
What makes a variable?
Yeah, it creates something called M1.
So M1 is that
Yeah.
that simple logistic regression?
Yeah, it's the model, yeah.
And you can call that whatever you want.
Call it whatever I want. I called it M1 for Model 1. I could have called it Fred. Remember, I could have come up with different names like Jennifer, and Barney, and Wilma, and Rebecca, which was just weird. Okay, so the first command I'm going to submit is called estat classification. Estat classification. And this ought to look pretty familiar to you guys in interpreting tests. All right, so what do I have here? I have sensitivity, specificity, positive predictive value, negative predictive value, right? So it does all of that work for you. So what it's going to do is it's going to say, okay, it's going to arbitrarily pick the probability of 0.5. So if you have a predicted probability of 0.5 or higher, it's going to predict you being positive, otherwise not. You can change this value, but Stata as a default value is going to set it to 0.5. Okay? So anybody, if we use this as a clinical decision rule, like maybe a CART analysis or regressive partitioning, maybe you've heard of that? Maybe one of your colleagues gave a presentation on that last week?
I did journal club last week.
Journal club last
I would
week?
say I gave a presentation on journal club.
It would be the idea.
I just needed a crash course in order to stop tomorrow.
Well, anyway. So here, our model's terrible. All right, this model's just god-awful if we set a cutoff criteria of 50%, because the only thing we get right is specificity, and God, who cares about specificity? I'm not even sure why these things were developed. They're so misleading. People are so confused by them. These are the only two things that are any good for any kind of decision making, right? These are nice population level statistics. Who cares? So I don't get anybody right. I don't predict anybody who's going to have low birth weight, and I only get 2/3 right when I say no, you're not going to have low birth weight at a probability of 0.5, right?
So the probability of 0.5 is the probability of what?
So what will happen, this is the outcome of my model. I'll have, I forget what the coefficients are, but I'll have my beta 0 plus my beta 1 x, right? This is going to give me my logit y. I turn my logit y into a probability, right? If the probability is greater than 0.5, then we would say, what's our cut point in our model for saying that if somebody has a probability greater than or equal to 0.5, we're going to classify them as most likely to have low birth weight. This 0.5 is arbitrary. I could say 0.25. Anybody with a probability of greater than or equal to 0.25, I'm going to classify them as most likely having low birth weight. The reason this...
So why would you pick one over another?
Well, this is where subject matter expertise comes in, and the quality of your model, right? Because...
Well, you're picking sensitivity and specificity when you do that, right?
Yes.
You're deciding where you put your cut.
Yes.
Yeah.
And this is where I want to go to next. Well, there's something else before I get to that, but since you're talking about that, if you type in LROC, I'm sure you've seen curves like this before. This is a receiver operating curve. You've seen this before, sensitivity, specificity. This model sucks.
What does that look like? You want to...
I want it to look like that.
Oh,
I want...
Yeah.
Ultimately, the perfect model would look like that. It would capture 100% of the area under the curve. Whereas here, we only capture 55% area under the curve. So if I were to flip a coin, I'm doing no better than 5% better than flipping a coin. What good is that? You know, it's not terribly useful. Right, so all that stuff that you learned way back when comes back to roost. Huh? You've seen this stuff. You've all seen this stuff before. Just lie to me and say, oh yeah. I'd be really concerned if you've never seen this before. The other picture I can draw using L-SENS, L-SENS, is this gives me my sensitivity and my specificity, right? Using a cutoff of whatever. So probably if I wanted to maximize my area under that curve, I would want to figure out where's the point at which these two things cross. That would maximize the area under the curve. However, in medical decision making, I'm going to make the assumption that you've heard about you want to either maximize some function or minimize some other function. That's how you would make those decisions as to where to put the cutoff in your model, right? But from a statistical, mathematical point of view, we can find the point at which we maximize the area under the curve. However, you know, there's like the whole breast cancer screening debate. You know, how much money do we spend for that number of women, incremental number of women that we catch, kind of thing. In clinical trials, we talk about number needed to treat before we get some benefits, right? If the treatment is very, very expensive, we have from a societal perspective, we think about, well, if it costs $10,000 per treatment or $100,000 per treatment, that would mean I have to successfully treat X number of people before I see any cost offset kind of a thing. Right? So this is purely statistical, what we're looking at here. Okay. All right. So now what I want to do is let's add another thing to the model. So now what I'm going to do is I'm going to add mother's smoking status to the model. This has nothing to do with the attractiveness of the mom. This has to do with whether or not the mom smokes. So now what do we see? Finally, yay. We get a significant p-value, yay, worship at the altar of the p, yay. All right, and now what do we see? Well, we still see that age is still inversely related to the probability of low birth weight. Now smoking has a positive logit. So what would we interpret from that, just looking at that?
More smoking, more birth weight.
All right, so if you smoke, if the mom smokes, that's going to increase the probability of a low birth weight. So now, writing down this equation becomes more important because now I have a model. If I wanted to find the probability or the odds of a mom, of a given mom, some mom, how old was your mom, the last mom who came into your clinic or wherever? Make it up.
25.
Did she smoke?
Sure.
Okay, so now we can say we have this 25-year-old woman, so we have 0.06 plus negative point, I'm just going to call that negative 0.5. And you said she was 25 plus 0.69 times 1, because we're going to say smoking is 0 and 1, right? This becomes, if I were to exponentiate that, that becomes the odds of that mom having a low birth weight baby. All right? So does that answer your question? Okay, good.
Is it negative 0.05?
Yeah.
Yeah, that's a negative here, 0.5.
0.05.
Oh, 5.
Oh, sorry. So you were saying that the pseudo R squared is kind of like the R squared?
Yes.
So can we say that this represents
represents 3% or something.
Yeah, it's sort of 3% of the variability in that outcome. Because I can still compute variance, right? Except in the linear model, we have that straight line assumption. Now with logistic regression, we're saying no such thing with a straight line. So people interpret it as like an R-squared coefficient of determination. Strictly speaking, it's not. It's an approximation.
Those don't get reported more frequently. And then what's like a good value, or that depends on your field?
It depends on it. Right, there are other statistics that we can look at. But anyway, are you starting to get a sense of why we need to understand this? Because now we can get, okay, 25-year-old smoking mom, this is your probability of having a low birth weight baby, as opposed to the 30-year-old non-smoking mom. Okay?
And what do the coefficients represent again?
Those are changes in the log odds.
Okay, change.
Right? So think of these, you have to remind yourself, these are logits.
Right.
To make these somewhat meaningful, I have to exponentiate them.
Got it.
To turn it back into something that a human understands.
Right. Okay.
Right? But we know we can just look at the signs to give us a gross sense or a coarse sense of positive or negative effect on the likelihood of the outcome.
And the absolute value of them doesn't matter.
Well, it
Just
does.
like-
The closer to 0, if I were to exponentiate 0, that's going to give me a value of 1. So then that means it's a 50-50. It has no effect, no real effect on the probability, on the outcome. Whereas the farther I go away from 0, here, the stronger the effect in some sense. But remember we talked about covariance versus standardized values? I could put something like brain size again in here, which has a ton of variability in it, right? So I could imagine brain size having a small, very tiny coefficient, but people's brain size don't change from, mine and your brain size don't change from 1 voxel, 1 and 2. Like the difference between mine and your brain size might be 10,000 voxels. So for every 1 unit change, in this case 1 unit change in voxels, the effect of that 1 voxel on the outcome would probably be infinitesimally small. However, 10,000 unit change, now we're talking something, but that's real differences.
I mean, can you use that the same for every 1 change in
That's exactly how we interpret it.
low birth weight? You have a negative 0.05
Logit
logit.
change.
Okay, change.
Yes, that's exactly how
So
we
you
change
can
it.
say from this table that smoking has a higher
Not necessarily a higher.
or a greater impact.
Smoking increases the odds.
More than age.
Not necessarily age, because we have to take into it, this is a binary variable, and that can only take on the value of 0 and 1.
Yeah.
Age can take on anything from, I don't know, what's the youngest people you see in your clinic, 12 to 56, or whatever, Right?
Can you separate those out by doing the
Oh, like we did we can
like
look at,
XI and then I, and then you separate them out by age group or something?
so you want to break them out by age group, I'm not sure.
I don't know, because are you treating age as a dichotomy?
Continuous variable.
As a continuous variable there, okay.
Yeah, can I treat age as a categorical variable? Sure. I can.
Yeah,
But here I'm choosing to treat it as a continuous variable.
okay.
Yeah.
I mean, isn't it hard then to compare, like a binary variable to,
Yeah.
so like you can't really do
Not
that?
really. It's difficult compared to what we did in regression, linear regression, where I can just turn everything into a z-score.
Is it easier when you break it into a categorical variable to compare?
Not necessarily,
Okay.
right? They're different constructs in that case. I see what you're trying to get at.
I'm just trying to see how to when you have a whole list of variables or predictors,
How do you choose them?
how do you kind of look at them
That's what we're going to do
together?
next.
Okay.
So remember I
compare them.
stored the effects of the first model, and I also stored the effects of this model. So that first model, that simple model, is nested within this model. And now I can ask the question, does adding this variable, age, smoke, whatever the hell I put in here, does that add significantly more predictive power than the simpler model? Does that make sense? So we're saying, is this new, more complicated model? We're basically going to ask the question, is it worth it to make the model more complicated by adding more variables? That's what we're saying.
Can't you tell that by like the
No, what it's going to look at,
probability?
it's going to look at these log likelihoods. So what's going to happen is it's going to look at the difference between the negative 2 log likelihoods. So it's essentially going to take each of these log likelihoods from the model, multiply it by negative 2, and then take the difference between the two models. And then what it'll do is it's going to look at the difference in the degrees of freedom. From the previous model, if you remember, we had 1 degree of freedom from our likelihood ratio, from our chi-square. So the difference between the first model and the second model, we fit 1 more parameter. So we're going to say, is adding this new parameter, did that add significantly to the model?
You can't tell anything by looking at the fact that you had an insignificant p-value before, and now you have a p-value that's below your threshold for significance.
Well, yeah, probably, but this is a pedagogical.
This is more precise.
Yeah.
So if you had like 5 variables,
Yeah.
would you do that for each? Would you start with 1 and then stack?
I would do exactly as we described in the beginning of the semester. I'd probably start with my demography variables, and then I might start with my clinical variables for which I don't think my intervention is going to have any effect, and then I will end with my most important variable. So then I would look at the incremental change, and I would say, okay, now that I've taken all of these things into account, adding the thing that I'm really interested in, does that have an effect on the outcome? It's exactly the same thought process as we did before.
So you create your model and say, I think these are all the things that are important, and then you put them in order of least to most important,
Yeah.
and then do.
But I don't have to put them in one at a time. My demography could be age, smoking, blah, 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 right? I could fit all of those first. I don't care about the outcome of that model per se. What I want to do is then compare this model against that model, and then this model against this model. Right?
So let's say you have 2 things, ultimately in the end, that you think are really important. Would you try
I would put them at the end.
both ways? Like
Yeah.
kind of try one first and then try
Well, if I had a theory or a hypothesis that both of these things are important,
yeah.
that's a different question than, are either of these things important? Because what you're asking is, well, you're asking are both important as opposed to are they individually important? Because remember, both of them can combine to be even more important as they would be individually. So this gets back to the idea of what's your question. So really, this concept here, we're not learning anything new, except now we have an interesting way. Instead of looking at changes in R-square, now we can look at likelihood ratio tests. Okay? Now to do that likelihood ratio test, I just do LR test M1, M2. And this is going to allow me, this test simply compares model 1 versus model 2. And it's going to say, okay, that likelihood ratio, the difference in the negative 2 log likelihood, many times you'll, well, in some statistical packages you'll see, you won't see anything because that's the dead soldier. You'll see something that says negative 2 log likelihood. The log likelihoods for this model, for the second model, is 113.64. The log likelihood for the first model was 115.95. The difference between those two models was about 4.64. The first model used 1 degree of freedom, the second model used 2 degrees of freedom. I subtract 1 from 2, I get 1 degree of freedom. This difference between the log likelihood, we believe, are chi-square distributed. So this is a chi-square statistic based on 1 degree of freedom, and we say, you know what? Yeah, adding smoking status was a good thing. It added statistical benefit to the model. And all of those things that I did before, if I do L rock,
Wait, how do you know that it added?
pardon?
How do you know that it added? What are you looking at?
Oh, okay. So this is the difference between the two models, the -2 log likelihood between the models. This is a chi-square statistic based on 1 degree of freedom. This is the p-value for this chi-square statistic based on 1 degree of freedom. So this is statistically significant. What we're testing is, the null hypothesis in the likelihood ratio test is, adding the new variable does nothing to the model, does not significantly improve the model. That's the null hypothesis.
Oh, yeah, okay.
We're rejecting the null hypothesis that adding, making the model more complicated, does not add to the model.
What is the advantage of doing this over putting all your variables of interest in the model and
Yep.
seeing which ones are like significant,
Okay.
and assuming the ones that aren't significant don't contribute to?
So what you just described is something called the direct regression. So you just added everything into it, right? What you have, by doing what you described, this direct regression, you can't answer the question, what is the incremental effect above and beyond all those other variables of the real variable of interest,
Gotcha.
right?
Okay.
So it doesn't answer that question.
So, and this might be the wrong place to ask this question, you can tell me that if you want to talk about it later, but like some people will check each variable and see on like univariately if it's contributes or if it's significant, and then just use the ones that are significant in their final model, and some people just use all the variables. Can you talk about the difference between those approaches?
Sure. The first approach that you just described is old school. And
Each one.
yeah, looking at things in a bivariate sense, you mean not univariate, right?
Yeah.
But we learned about the issues with that when we did partial and semi-partial correlations. I remember we looked at like age, speech rate, and memory span or something like that. And all of the bivariate correlations were positive and what we would consider to be large, right? Right, so we'd say, oh, all of these things are important. But then when we put them together, we saw age, for example, became very small and negative. When you look at things univariately, you're, in some sense, omitting important variables. And remember, one of the assumptions of these models is that you're not omitting important variables. So, looking at things bivariately, other than looking for collinearity and suppression, which, by the way, is alive and well here, I don't know what that actually adds. I just think that's how it was taught before people thought about things like partial and semi-partial effects. Right? Because if you could omit, you could take out something that is bivariately not important, but that's not what we're doing with multiple regression. Because it could be that that non-significant bivariate relationship becomes really important after I've partialed out the effect of all these other variables. Because that bivariate relationship, or the variance that what looked like an unimportant variable, now becomes really important. So, remember when we talked about this stuff, right? Let's say that this is y, this is x1, and this is x2. And let's say that x1, the relationship between x1 and x2 in a bivariate sense, doesn't look significant, right? In multiple regression, and this is multiple regression, x1 and y is not what we see in the multiple regression. What we see is the relationship between x1 and y prime. So the absolute area doesn't change, but the relative size of that area does change. So if I don't include x1, I may be saying, you know what, oh, x1 isn't related to y. But in fact, it is once you've taken into account all those other variables. Which is why in the beginning, I encouraged you guys to think about theory building and think about classes of variables.
Are you going to go over how to look for suppression?
Same thing. Nothing changes because it's regression. Right? You want to look for influence variant values and everything. Nothing changed. The only thing that really changes is the homoscedasticity assumption. Okay. So now this becomes our ROC curve. Right? And now we're beginning to see some separation from the 45-degree line. Right? There's never enough time in here. So what I can do now, and this is to, what's his name? Sam, this is to your question, Sam. What are the marginal effects of smoking? So this is the effect of smoking on birth weight, adjusting for mother's age. So it's just like we did before with regression. I'm going to use adjust smoke, and I want to get a confidence interval. These are now logits. So what it's going to do is it's going to fit the value. It's going to, it's the same model. What it's going to do is, let's say beta 1 is smoking and beta 2 is age. What it's going to do is it's going to say, okay, it's going to set the value of age at the mean value of age. This becomes the effect of smoking at the average age.
And if there were multiple variables,
it would adjust for everything else in the model at the mean of all of those values. Okay? Okay. I'll just start getting into this. This stuff. All right.
So that logit coefficient there is different than what you get if you just do the logistic command?
Yep.
Okay. Yeah.
Right? It was like 8.5 or something like that, the adjusted command.
Yeah.
So what it's going to do really, it's basically going to fit this model for you, and then it's going to say, okay, what do you mean adjust for age? At what age do you want to look at the effect of smoking? So in adjusting, unless you tell it at what age, it's going to find the average age and plug that in here. Add them together without exponentiating it. That becomes the adjusted value. Because it's going to take into account the intercept, the effect that you want, and the effect of the other variables at their mean values.
Do you otherwise, you can otherwise put in that equation age equals 50? Or
Whatever you want, yeah. Absolutely.
Do you do it if or just?
Pardon?
Yeah.
How do you do that?
Yeah, I didn't change the age at which it looks.
I think you type at. Just smoke. Yeah, it's there's a way to do this. There you go, right there. So what I did was I set the value of age to be 30. And that becomes the effect of smoking at the age of 30.
And the logit's -1.
Right. makes sense, right? That makes sense because the higher the age, the greater the protection factor, right? So now if I do that same crap, logits, Belgian model, low. So now I set age to be 23, da 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 da. That's the same value we got before, right? Right? The same value. So that's how, if I want to get the age of the 25-year-old smoker, that's how I would get that person's logit. Exponentiate that value, get the odds, take those odds, turn it into a probability. Make sense? Okay. All right. You guys are asking good questions, which is why we always run out of time. Should we keep going until Andy kicks us out? Yes? I mean, we don't have to. I'm not going to hold you. All right. Let's keep going. Okay, so now what I have is what I can do is I can honk. This function is our logistic function of probability of a birth weight with an upper and a lower confidence interval around that logistic function. So what's crazy about here? You know, I started off at -40 and I went to +40. That kind of doesn't make any sense. The reason I did that was to see that that function that we created is that S-curve that we talked about last week. If I truncated it at the 18 or whatever the minimum age was, you wouldn't see the S. And you'd be like, hey, Tim, what's all that S thing that you're talking about? But you can see how, if you could imagine that as age went out this way, it asymptotically gets closer and closer and closer to 0. And as age goes that way negatively, it asymptotically gets closer and closer to 1, right? Okay. So you can actually now visualize the relationship between age, smoking, and probability of low birth weight, right? That's what we're looking at here.
Is there a way to do that shorthand without having to?
No, unfortunately not.
What's that 0.391 in there? You're multiplying that coefficient for the smoking times.
This is our regression equation.
Where are the 0.391?
Those are probably the upper and lower confidence limits. Okay, now let's add hypertension to the mix. And now I can compare, adding hypertension to the second model, right? So now what I'm going to do is I'm going to fit hypertension to the model. Oop, what happens to the effect of smoking? Becomes non-significant, and this is why you don't do this in a bivariate sense, because things change in a multivariate sense. Now the effect of age, well, that's still negative, but it's getting close to 0, right? The effect of smoking, well, that's starting to lessen or increase, I don't remember. But it's now, well, that's still significant. And now we look at hypertension, right? Ooh, hypertension, is that right? Hypertension, you would believe, is related to low birth weight. Now I look at this. This is a logit now. Now if I exponentiate a value of 1, it's going to be big, right? So now we're saying, what's the effect of adding hypertension to the model? That adds some statistical prediction power to the model. So we're making the decision. It's adding hypertension to the model is a good thing. It's better than not adding it. Now let's add race.
So as long as the p-value is significant, it doesn't matter how significant it is?
Well, this becomes the difference between statistical significance and clinical significance. But I would say that something with a logit of 1 is really humongo.
But in terms of the model,
Oh, no,
so
it's...
it's like, it doesn't matter if it's 0.03 or 0.01
No.
or whatever.
Right? Good question. So now I'm going to add a categorical variable in here with more than one value. So just like we did with regression, we did the ANOVA in regression, I'm going to use the XI command, and I'm going to say race is now a categorical variable. It looks like we have 3 levels of race. Right? 3 levels of race. Ooh, what happened to hypertension? No longer significant. Oh, what happened to that? I don't know. Smoking is still significant.
Odds ratios there?
Yeah, these are the odds ratios.
No, why did we switch down?
I don't know, just show that you could.
Okay. Numbers are all
But I don't know how to interpret these 2 and 3. I'd have to go back and see how the data were coded to figure out what the reference group is. Because I can actually directly compare race 2 and 3. I can see if they're different. But I have to take an extra step. These compare the effect of whatever race 1 was compared to races 2, race 1 versus races 3. Whatever races 2 and 3 are, they are more than twice as likely to have a low birth weight baby as compared to someone in race 1 holding these things constant. Right? And that's how I would interpret these.
I mean, when you're storing the estimates, it doesn't matter if some of them you run as the logit OR and some you run as...
Because it's the same. It's just doing transformations on those numbers. Okay. And we see adding race. That's statistically significant. That's a big chi-square statistic. Now what I can do is, for reporting purposes, I can now print out the results of all my models. So this is the logit for age. That's the standard error. That's the z statistic. This is the p-value for this coefficient. Now remember, these are logits. At least I think, no, they're not logits. These are odds ratios. Right? And here are my constants. So here are my 4 models. This model is nested within this model. This model is nested within this model, and this model is nested within this model. So this gives you a really interesting table to show people this is how you maybe arrived at your final model. Here are the chi